Okay, so today I'm going to present how to solve problem 16 on the 2017 FMA exam. There are two ways I'm going to show how to present it. One way is the way they recommend. Another way is what I came up with using limiting cases, which is a really useful thing on these competition problems. So let me start off. So it asks, a rod moves freely between the horizontal floor and a slanted wall. When the end is in contact with the floor is moving at v, what is the speed of the end in contact with the wall? Now when I first saw this, I thought it might be like a calculus problem. You could solve it with calculus. You take the derivative and you find instantaneous rate of change on both ends. But they wouldn't put a calculus problem on the FMA, so it must be able to be solved without that. So what the first thing I do is find out what's the same. So we can say that the rod is going at some velocity v here, and then some velocity u here. Those aren't necessarily the same, especially considering all the solutions we have are different. So that wouldn't be a reasonable way to solve it. But what do we know is equal? The rod doesn't stretch or squish, so these two must be the same. These two components of the v and u. So if we can set these two equal to each other, then we should have the solution. So let me just draw the components also, maybe in a different color. So there's two components to the u and v vector. So now we want to find the measurement of this and the measurement of this. So for this one, it should be easy. We have v here, then because this is an opposite angle to that, must have theta, and then we have this component, which we need. And so it's on the adjacent side to this. So that's cosine of theta times v. Now we set it equal to the other side. Now this one is a little bit harder to calculate. This one should be easy to solve, especially if you're good with angles. So I'll walk through this one. So we have alpha here on this side. And that, since this is a 180 degree angle, this other side should be 180 minus alpha. And that means since this is theta, if we want to find this angle here in the corner of this triangle, we just need the sum of a triangle is 180, and that equals 180 minus alpha minus theta, or plus theta, and then plus some angle that for here, which I'll call beta. So if we solve for beta, we'll get beta equals alpha minus theta. Okay, so there we go. We have the angle here. And this is also a cosine because we're taking the adjacent angle to this. So let me move this. Okay, so do I remember what we had first was v cosine theta. And now we have this new velocity u, which we don't. That's fine because this is the formula for it. So u cosine of alpha minus theta. Now we take a look at what the problem is asking for us to do, which is find u, which is the speed that in contact with the wall. So if we solve for u, we get u equals, divide cosine of alpha minus theta on both sides, v cosine theta for cosine alpha minus theta. And that should be answer D, which is the right answer. Now this method is kind of challenging, mostly because it requires you to make this connection, that these two are equal. There's a better way for me to do it, at least. That makes sense. That makes you just think about how this could be realistic. Think about it in a realistic way. So let me clear up the board for this. Okay, so let's instead test some limiting cases. So what I first thought of is, what if alpha equals 0? What if theta equals 0? What if we just have flat? If you just say pull this side with velocity v, then this side will just pull with velocity v. Okay, so this means given alpha equals 0, and then given theta equals 0, the velocity equals is just the velocity of the other end. Okay, so where does theta and alpha equal 0 cause the expression next to v equal 1, because then we just get v. So that would mean the denominator doesn't matter to some extent. Mostly, as long as the denominator doesn't equal 0, which we'll check, the numerator just has to equal 1. Cosine is 1, sine is 0. So we want it to equal 1. So we want 1 over 1 on one of these. So for the first one, we have 0 over 1, because alpha 0 minus 0 is just 0. So this would end up as 0, which means not a. Same thing here. Sine gives you a 0 on the top. Doesn't work. This one, cosine gives you a 1 on top, which is good, but then the sine gives you a 0, which means it would be going at it'd be approaching infinity, or depending on the direction. So definitely not this. D seems like a good candidate because we have cosine over cosine, which is 1 over 1. That one looks good. And E doesn't seem right either. Sine on top means we'll get 0 at the end. So already we've eliminated everything, and we've resulted in D. Okay, and through this we saw that D is the only one that works. So this is a very good time. This seems like a very good problem to test out using limiting cases, especially if you're cut for time, because even as slow as I did it, it's very fast. You can find it if you find the right cases, especially this, because this showed that all of the others didn't work. Although you can employ different types of limiting cases. Like you could prop the stick on here. That's what I did, and I also ended up with D for that. And yeah, so it's better to combine them too, because then you can sort through them and see which one's better, which one works right. So yeah, that's what I hope to show you, how to use limiting cases to make this problem a lot easier. Thanks for watching.